Which of the compounds below exhibit predominantly covalent bonding? Now, you should be able to predict this on your own, not given electron negativity numbers, okay? But if you did have them, it's a little bit easier. So I'm going to do them with electronegativity numbers, but then I'm also going to talk you through the trends of it. Hydrogen, electronegativity 2.1, chlorine, electronegativity 3.0. Difference 0.9, which is called polar covalent. Again, if it's between 0 and zero point 0.4, it's purely covalent. If it's between zero point 0.4 to 2, it's polar covalent. And if it's above 2, it's considered ionic. So I'm going to do them all by numbers, and then we'll talk through without numbers listed. Magnesium, electronegativity of 1.2, chlorine, 3.0. Difference here, 1.8. It is polar covalent, but it's almost ionic. And remember, we talked about bonding as a spectrum. So we say it's polar covalent because it is actually sharing a little bit here, but it's also very, very close to being ionic. So it is all the spectrum. It's not just a black or white answer here. If I did ask, though, technically speaking, this would be polar covalent. Without numbers, I would expect you to tell me ionic. Okay. Sulfur, 2.5. Chlorine, 3.00. Difference here, zero point 0.5. It is polar covalent, but almost nonpolar. And PCl5, phosphorus 2.1, chlorine 3.00, 0.9 difference, polar covalent. So which one exhibits predominantly covalent? Well, that would be the one that's closest to actual nonpolar. This one has the most covalent bonding to it, SCl2. Now, again, we had numbers here. And if I gave you something like this where they were all very similar like this, I could give you numbers and you would have to know that. What if you didn't know numbers? How would you do this? You need to know that first place for electronegativity goes to fluorine. Need to know that second place goes to oxygen. Need to know that third place is tied between chlorine and nitrogen. Okay. After that, you need to know the general trend across and over. You should also know that even though hydrogen fits over here, that hydrogen and carbon is nonpolar. So therefore, hydrogen must not follow the general trend of up and over. With that in mind, with the up and over idea, I know chlorine is in third place. All of these are bonded to chlorine. Okay. So therefore, I can think about the fact they're all bonded to chlorine and think about where they reside on that table. Now, I may not be able to know hydrogen compared to sulfur or phosphorus because all I know is that hydrogen's close to carbon. When I look at the table, let's say carbon's right here, phosphorus is here, and sulfur's here. By general trend, I may not be able to know the HCl one, but I should know that sulfur is more electronegative than phosphorus by general trend. They are one spot lower than the carbon, which is similar to the hydrogen, but the hydrogen is way over here. So I would expect the hydrogen to be more different than the phosphorus or the sulfur because of where it's located on the table. And I would expect the magnesium to have the largest difference because it is a metal. So you should have a general idea, even if not given the numbers. If given the numbers, you should be able to tell me exactly what it is. What's this one? Phosphoric acid, H3PO3, or sorry, not phosphoric. I'm still used to saying phosphoric. Phosphorus acid, H3PO3, has the structure HO2PHO, in which one hydrogen atom is bonded to the phosphorus atom. Two hydrogen atoms are bonded to oxygen atoms. For each bond to a hydrogen atom, decide whether it's polar or nonpolar. Assume that only polar bonded hydrogen atoms are acidic. Write the balanced equation for the complete neutralization of phosphoric acid with sodium hydroxide. A 200 ml sample of phosphorus acid requires 22.50 mils of a 0.1250 molar NaOH solution for complete neutralization. And what is the molarity of H3PO3 solution? Okay, so pulling in some stuff from a previous semester, we can do this. So phosphorus acid, H3PO3. It is telling me that I have one hydrogen bonded directly to the phosphorus. I have two hydrogens bonded to two oxygen atoms. So that third oxygen must be bonded directly to that phosphorus. It's the only place for it to go. Everything needs its octet. For each bond to hydrogen atom decide whether it's polar or nonpolar. Okay. So phosphorus has an electronegativity of 2.1, hydrogen also 2.1, oxygen 3.5. The difference here between phosphorus and hydrogen is 0, nonpolar. It's actually called pure covalent as well, but it is a nonpolar bond. So just to answer the question, it's nonpolar. To be more specific, it's pure covalent. This here and this here have a difference of, what is that, 1.4? So that is a polar covalent bond. Again, without numbers, I wouldn't be able to tell you for sure the phosphorus and hydrogen bond was nonpolar, but you should know that oxygen and hydrogen are going to be polar because that is a large separation in the periodic table. Oxygen's second in place for electronegativity. It's going to be polar when it's bonded to oxygen. Okay, what's the rest of the question? Assume only the polar hydrogens are acidic. Okay. That means that this is acidic and this is acidic, which means these are the two protons that can be removed if reacted with a base. This proton can be removed and this proton can be removed. Remember when I say proton needs to remove because they're removed as an H plus, they leave their electrons behind. So that means only hydrogens bonded to the oxygens are acidic. Hydrogens bonded to the phosphorus will not be removed. Okay. So let's write a reaction. H3PO3 is going to react with NaOH. It's going to remove two of those hydrogens. So it's going to form Na2 HPO3, because again, if this removes two, I'm left behind with HPO3 2 minus. So I have two sodiums to counteract that charge. All sodium salts are soluble, and then water. Balance this out. I'm gonna have a 2 here and a 2 here to balance it out. So I've got my balance reaction. What do I want to know? I want to know the molarity of that phosphorus acid solution. So the number of moles of H3PO3 per liter of solution. We've got in here, it tells me that I'm using a 0.1250 molar sodium hydroxide solution, which is 0.1250 moles of NaOH per liter of NaOH solution. And I use 22.5 milliliters of it. So 0.0, I apologize, I really cannot write that well on my screen. 0.2250 liters of the NaOH solution. Now, if I look at the balanced reaction here, I see that for every 1 mole of phosphorus acid reacted, 2 moles of sodium hydroxide are also reacted. So it's a 1-to-2 ratio. At this step right here, this would cancel my liters of hydroxide and my moles of hydroxide. I'd have moles of phosphorus acid, but I don't want moles, I want moles per liter. So I'm going to say times 1 over 0.200 liters of the phosphorus acid because it says that I'm reacting 200 milliliter sample of that phosphorus acid. This gives me a concentration of 0.00703 molar H3PO3. Let me check. I need one more sig fig on that. So let me check my calculator quick because I definitely need one more sig fig and I want to make sure to give you guys the right sig figs. I don't know if it's just a 0, if there's actually a number after that. So 0.1250 times 0.0225 divided by 2 divided by 0.2000. All right, I'm trying to put this in my calculator, but I'm doing it on my computer, which is not as easy to do for me. Okay, so you need an extra zero there because of sig figs. 0.007031 molar is the correct molarity there with sig figs attached, because we do have 4 sig figs here, 4 sig figs here, and 4 sig figs here. So we do need 4 sig figs overall. What about this one? Of the atoms listed below, which is the most electronegative? I don't know why there's a random 2 there, so we're just gonna pretend there's not. Okay, first thing I do is I look for the ones I have memorized. Fluorine? Nope. Oxygen? Nope. Chlorine? Nitrogen? Nope. Yep. Nitrogen's third place. It's gonna be nitrogen. I don't even think about the trend. I just look for them. What about this one? Which of the bonds below is expected to be the most polar? CH, NH, CLH, HH, or OH? Okay, they're all bonded to hydrogen. So really, I just have to think about the trends. So I think, well, is there any fluorine around? No. Is there any oxygen around? Yep. Oxygen's the second most electronegative element there is. That's going to be the most polar. It's going to be the biggest difference because it's second place for electronegativity. So because everything else is paired up to hydrogen, that's going to be my answer.